One pretty bizarre theory claims that space is water, and we're here to figure out whether it's a legit scientific idea or a fallacy resulting from myths and legends. Spoiler alert, you might be in for a surprise. Space is an almost perfect vacuum that has an extremely low density of hydrogen molecules, helium, dust particles, and plasma. As for water, it consists of hydrogen and oxygen. While hydrogen is the most abundant element in the universe, as well as the main material for the formation of stars, oxygen in space is mainly formed by the fusion of helium and carbon nuclei. It happens during the nuclear fusion process of stars that can be at different stages of their evolution. No wonder that there's much less oxygen than hydrogen in the universe, but it's still enough to form water in different states. For example, water molecules can be found on dust particles in molecular clouds, cold and dense regions of outer space. They are also present in interstellar space. There, they take the form of gas or ice on the surface of comets, asteroids, planets, and moons. The surface of some satellites of Saturn and Jupiter are covered with ice crust under which there's probably liquid water. Venus and Mars have gaseous and liquid water in their atmospheres. On our home planet, water covers more than 70% of its surface. In other words, space is filled with water, but it's distributed extremely unevenly. Interestingly, people started to compare space to water long before they found out what the cosmos was actually made of. The very theory that space is water dates back to the times before the current era. For example, some ancient civilizations believed that the ocean was a portal to space. Of course, in the physical sense, there's no direct connection between these two. But both represent a huge space with different mysterious inhabitants which people have been trying to study for a long, long time. People in the past believed that the ocean and stars were linked. Thousands of years have passed, people have mastered sea navigation, but we still haven't solved all the mysteries of the deep sea. Just like we don't know all that much about space. What giant monsters can be hiding in its depths? Only 2 to 5% of the world ocean has been explored, and space has been explored by the same percentage. For example, dark matter, making up most of the universe, is still a mystery to us. Of course, in a physical sense, space doesn't behave like water. But both water and space are fatal. Without a special suit and equipment, you won't be able to breathe, and there's also decompression sickness threatening your life. Only in space, it's a lack of pressure, while in the depths of the ocean, it's either too much pressure or a dramatic pressure drop due to the fast rise from the depth to the surface. Even if outer space is not water, could it be liquid? One study suggested that the vacuum of outer space could be a dilatant fluid, also called shear thickening fluid. This theory is based on the so-called Pioneer anomaly, a decades-old astrophysical mystery involving two NASA space probes. In the 1970s, two NASA spacecraft, Pioneer 10 and Pioneer 11, started their journey toward Jupiter and Saturn. Observing their trajectory, scientists from NASA noticed that the probes started to slow down. Of course, the scientific community began to offer different hypotheses. One of them suggested that thermal radiation emitted by the probes in space could have created some pressure on their surface. It could be slowing down their movement. Eventually, after additional research, it was concluded that the physical vacuum most likely behaved like a dilatant fluid when the shear stress increased. Later, another scientist managed to find some proof that spacetime can behave like a fluid. You see, according to Einstein's theory of relativity, spacetime curves around mass and energy. That's what leads to an effect we know as gravity. But apparently, if you write down the equations of sound waves moving in liquid, they will look the same as the equations of waves traveling in a gravitational field. Such a mathematical relationship between fluids and gravity is called analog gravity. The researcher also managed to recreate these gravitational analogies in a lab. At the moment, the results of these experiments are still controversial, and many scientists don't support this theory. Even so, maybe the idea that outer space is liquid isn't so unfounded?
About 71% of our beautiful planet is covered with water. That's why you see the coolest blue color when you look from space, compared to all the other planets in our solar system. But we're still not sure how exactly we got all that water. And what makes us so special that we ended up the only ones with water on the surface and life? Some say the water has been here ever since our planet formed. Let's jump back to that chaotic period about 4.5 billion years ago, when there were clouds of gas and dust swirling across our solar system. So, somehow, water molecules settled from all that chaos and just stayed there. Land mammals dominate our planet today, but we did originally come from water. So this was the main playground for creating life. Or maybe it wasn't quite like that. Some people believe that a long time ago, our planet didn't really have much water. That implies that all of our oceans formed from the water that came from outer space. Could it be that creatures from other planets sent it because they knew it was the key element for life to form and they needed friends? As far as we know, not quite. It's more like our water randomly came from asteroids and space dust. A Japanese robot brought tiny particles from one asteroid back to Earth, and scientists found something cool. They contained water. The water in these particles was probably created because, while coming from the sun, they were interacting with oxygen in space, and that way, we got water molecules. In the outer parts of the solar system where it's very cold, water forms icy objects, such as comets. As our planet moved around the sun, it collected these dust particles along with the water. Over time, this water fell from the skies and filled what we know today as the oceans. So maybe the water on Earth came from both these space dust particles and icy comets crashing into the surface. It's more probable than the theory that our planet had water even since the beginning because it was way too hot for water to become liquid. I mean, we have the best spot in the solar system for life because we're just the right distance from the sun for liquid water to exist. Any farther than that and it would be too cold and we would end up with ice only. Any closer to the sun would mean we'd have to deal with extremely high temperatures. We've already seen that happen to our neighbor Venus, the hottest planet in the solar system. But even though we had a great position, don't forget there was no atmosphere on Earth at its early stages, so nothing could keep that water in place. When our planet first formed, it was very hot and there was almost no air around it. The surface was like a melted rock. As it cooled down, an atmosphere started to form mostly from gases coming out of volcanoes. And it took about 500 million years for the surface of Earth to cool enough to keep water. So at those early stages, it was probably simply evaporating. If water really came to Earth later, comets and asteroids might have brought it here. Both types of space travelers came to visit once in a while, and both had enough ice to deliver the same amount of water as what Earth's oceans contain. This seems plausible, right? But we still don't know if it was an asteroid or a comet, or whether it was just one or many of them. Also, when exactly did all that happen? One way to tell which one brought us this magnificent gift is to look at the chemical composition of space rocks and compare it to that of Earth. One study showed that water molecules on Earth are very similar to the molecules of rock samples received from ancient asteroid Vesta. Vesta is the second biggest object in the asteroid belt, which is located between Mars and Jupiter. Only Ceres is bigger, and this one falls into the category of dwarf planets anyway. It's the brightest asteroid you can sometimes see even with the unaided eye. But the fact that water molecules are quite similar on Vesta and on Earth doesn't necessarily mean that Vesta was the one that brought water to us. It could be some other similar object that came from space. There are studies that have backed up the theory that asteroids brought water, like the one conducted by the Rosetta spacecraft, the first one that orbited a comet. It was also the first space probe that sent a lander to a comet's surface. Thanks to that, scientists found out that water on comets was heavier than most of the water on Earth. But then again, in 2018, there was a new study involving another comet that contained water with a similar composition as the water on Earth. What makes it different from the previous one? Well, here we're talking about a hyperactive comet. Such comets release more water as they get closer to the sun compared to regular comets. When one of those regular comets gets close to the sun, its ice turns directly into a gas, and this gas can later become liquid water on the surface of a planet. But a hyperactive comet loses not only ice from its center, but also icy particles from its atmosphere. These icy particles may be the reason why hyperactive comets have water similar to Earth's. There is water in other places across our solar system too, even though it's different from the water on Earth. It's often hidden under the icy surface of moons, such as Europa and Enceladus. Europa is Jupiter's most famous moon since scientists believe there's a giant ocean hidden beneath its icy surface. This ocean supposedly has about twice as much water as all Earth's oceans combined. And where there's water, there might be life. And who knows what type of organisms we might find there one day when we finally take a trip across our solar system. Scientists discovered this ocean using a spacecraft called Galileo. Galileo orbited Jupiter and detected a magnetic field around Europa, which was a sign there might be a big, salty ocean. The surface of Europa is covered with smooth ice, but it's full of grooves and cracks with strange dark streaks and reddish features. Scientists believe the moon's surface is like that because warm ice rises from deep below. Also, Europa's icy shell squeezes and stretches because of Jupiter's insanely strong gravity. This creates heat inside the moon, which is probably enough to keep the ocean in its liquid form. Then, we have Ceres, the only dwarf planet we have in the inner solar system. It's small and difficult to study. But a few years ago, the Hubble telescope found out it was actually more of a watery world than a rocky ball like everyone previously thought. And the story remains the same. The mantle is icy, and then there's a mysterious, slushy ocean underneath. Mars also has its own secret stashes of minerals that only form in water. And just like us, the red planet probably got its water from comets and asteroids that smashed into its surface. And it most likely had a lot of water on its surface, rivers, oceans, and lakes, but billions of years ago. That means Mars may have been a good spot to house life a really long time ago. But over time, the sun ruthlessly pulled away the red planet's protective atmosphere with the help of its rather unpleasant charged particles called solar wind. As a result, liquid water on the Martian surface either evaporated and mixed with minerals or went underground and turned into ice. And this leftover water is especially interesting because it can tell us if there's still life on Mars. Plus, if we ever move to the red planet, it would be good to have reservoirs of liquid there.
When you look at all the great emptiness between stars and planets, you think there's nothing but a vacuum. However, what if I told you that the universe is actually the crazy bubbly fizz of a freshly opened soda? And no, we don't mean just tiny invisible particles that everybody knows about. We're talking about invisible space foam. Let's check it out. Now, what is space-time? Not a simple question. The answer depends on how you look at the world. Right now, we have two titans of physics, quantum mechanics and general relativity. Now, general relativity is our old friend, made up long ago by the famous Albert Einstein himself. It tells us how huge celestial bodies interact with each other, how gravity behaves, and so on. It's standard physics that everyone's used to. On the other hand, quantum mechanics is a monster that clashes with general relativity in almost everything. This field is the rulebook for very tiny things, like atoms and particles. It also deals a lot with probabilities and uncertainties, all the weird, mysterious things in our world. The struggle comes from the fact that these two rulebooks, one for huge things and one for tiny things, don't match each other. They work separately, perfectly, but for some reason, they don't form the same big picture. Uniting them in one logical system is the hardest task for science at the moment. And while scientists are trying to unite these two titans of physics, we could unite our community. Just like or subscribe to Bridge the Gap. Share the knowledge with your friends as well. Now, let's go back to space-time, one of the most important things where general relativity and quantum mechanics clash. General relativity says that there are three dimensions of space, up, down, left, right, and back and forth, and one dimension of time. Space is simple. It's just basic geometry you learn at school. And time is a universal clock that ticks away at the same rate for everyone. Albert Einstein pictured space-time like a canvas, smooth, elegant, almost a fine piece of silk stretched out in all its glory. Celestial bodies hang out on this infinite piece of cloth, And the heavier they are, the more our canvas is stretched. Obviously, super heavy things, like black holes, stretch it very strongly, so all the little objects around them fall into this trap, as if it were some deep dent in a trampoline. It's a simple and beautiful explanation. But now, enter the quantum realm. In the hidden world of quants, things are not what they seem. Here, space and time go all wobbly. The particle movements are unpredictable. They jump up and down, doing unexplainable tricks and so on. Quantum mechanics also has its take on space-time, and a very weird one. Back in the day, a brilliant scientist named John Wheeler had a spark of genius. Maybe space-time isn't smooth and steady as we imagine, but more like a foamy sea with bubbles that keep forming and popping. There's a theory that in our universe there are tiny particles and their opposites, called antiparticles, which can pop into existence out of thin air, just like magic. When they appear, they touch each other, causing a mini boom, and then vanish just as quickly. We call these weird things virtual particles, and they kind of sound like bubbles, don't they? These particle bubbles are mysterious and fun to explore. We studied them a little, and we know that they can kind of chat with each other and don't like to follow typical rules of particles. For example, they have negative energy. It's especially weird that, in order to appear out of nowhere, they need some energy. And somehow, they borrow this energy from the vacuum, even before they're born. Basically, they take a tiny bit of energy from the supposedly empty space, and then, because they're good citizens, they give it back almost immediately. So, according to this theory, the universe is filled with lone-taking bubbles. And this disappearing act and energy borrowing is what we call vacuum fluctuations. You can see why Einstein would find quantum mechanics weird. Nevertheless, this is where the idea of quantum foam comes from. And don't rush to throw it away just because it sounds wild, but there are experiments to back that up. One experiment is called the Casimir effect. It's one of the most important proofs we have that those mysterious virtual particles are actually real. Imagine two metal plates hanging in a vacuum. There are no magnets around, no gravity to do the trick, nothing. But suddenly, these plates start acting like magnets, pulling towards each other. How is that possible? Well, a scientist named Hendrik Casimir from the Netherlands suggested that it's those playful virtual particles. Since they exist in a vacuum, they surround two metal plates. They want to go inside, right in the middle between the plates. But not all of them can, only the very important ones. These chosen ones, virtual particles, start bouncing between the plates like tiny ping-pong balls. Meanwhile, the other ones are crowding outside the plates. They want inside too, though. This crowd is getting bigger and bigger, and they start pushing and shoving, trying to sneak between the plates. And this is what makes the metal plates look like they magically attract each other. Now, this isn't the only proof of the existence of these virtual particles. According to Einstein, the light speed should be the same all across the universe. No exceptions, no matter what. It's always around 186,000 miles per second. But recently, scientists looked at super-energetic cosmic rays coming from very energetic galaxies. And they found that some of these rays didn't seem to follow this golden rule. For some reason, these energetic rays had a different speed. As you can guess, the quantum foam might be the culprit here as well. When these cosmic rays travel through the universe, they might encounter quantum foam. This foam would make their road quite bumpy, as if you were riding a bicycle through rubble, which is why the ride wouldn't be as smooth as they'd like. Little virtual particles appearing and reappearing again could give the rays particles a slight push. This could explain why they seem to break the universal speed limit. Well, it all sounds cool and dandy, but all the great quantum mechanical stuff always comes down to one problem: how to combine it with general relativity. These two things contradict each other once again. The famous string theory is one of the titans that tries to unite general relativity and quantum mechanics into one beautiful explanation. String theory says that the tiniest building blocks of the universe are not little dots like particles, but incredibly tiny strings. They vibrate and dance, just like the regular strings of a musical instrument. Each string movement creates a different particle or force, kind of like how different notes create different tunes. What's cool is that string theory has its own take on quantum foam. It suggests that the foam isn't just random bubbles, but it's also made up of these little strings. That would explain their existence and weird behavior. But so far, these are all speculations. First of all, we don't even know if quantum foam truly exists. It's a conclusion that we reached based on lots of data and observations, but there are no definite proofs of it yet. So, first of all, we need to see if it's really there, which is why scientists try to measure these particles to find them and their weight. Unfortunately, it's a bit of a struggle. This experiment would require a lot of effort and very precise equipment. If we actually find them, that would be a great discovery. It would help us understand space-time much better, clear some questions we have about the Big Bang and the early universe, and even stir up our visions of wormholes. In other words, these foamy fluctuations potentially could hold the key to time travel. So let's hope that one day we'll be able to finally find them and confirm their existence. Until then, keep exploring and stay curious.
Picture yourself floating through space during a casual spacewalk when suddenly your trusty helmet decides to take a vacation. Instead of freaking out and gasping for your last breath, you take in a lungful of fresh cosmic air. Now, let's dive into the mind-boggling consequences of a breathable outer space. On our cozy planet Earth, the air we breathe consists mostly of nitrogen and oxygen, with a smattering of other gases to keep things interesting. But beyond our atmosphere's 6,214-mile reach, molecular oxygen becomes as rare as a unicorn in a tuxedo. With an expanded atmosphere enveloping space, you'd be strapping on your space boots and jetting off to any corner of the universe, all the while breathing as easy as you do back home. Prepare your eardrums for a symphony of cosmic proportions. In the vacuum of space, sound waves can't travel because there's a serious lack of molecules to carry those groovy vibrations. Yet, in our newfound space atmosphere, the sound would have a field day, traveling far and wide. Get ready to tune into the sun and the other celestial crooners. The sun, in all its glory, would be rocking out with constant vibrations that would make your head spin. It would sound like attending a never-ending concert, where the sun's tunes hit your ears at a staggering 125 decibels, which is louder than 1,000 police sirens. In the absence of friction, planets and moons gracefully orbit the sun without losing speed. However, with the introduction of all that breathable air, things would take a wild turn. Planets and moons would be zooming through the atmosphere at super high speeds, resulting in some serious collisions with those pesky air particles. Brace yourself, because Earth would suffer the same fiery fate as those ill-fated asteroids entering our planet's atmosphere. Scorched surfaces all around. That's definitely not the kind of barbecue we were hoping for. And if that wasn't enough chaos for one day, get ready for the grand finale. Eventually, the moon would halt its celestial dance and come to a standstill, only to be pulled closer by Earth's gravitational force. This cosmic tango would lead to a catastrophic collision that could potentially kiss our beloved planet goodbye. Not to mention the rest of the solar system wouldn't be throwing a victory party either. All that air would wreak havoc, turning our peaceful solar system into a menacing black hole. The air would bring about a hefty mass, roughly 5 billion times greater than the Sun itself, spanning a mind-boggling radius of 90 astronomical units. If the Sun's gravitational pull decided to play tug-of-war with this colossal mass, the solar system would start to feel the squeeze. Compression madness. In the end, we might witness the birth of a black hole, a monstrous entity 1,000 Such a scenario is like trying to decipher a Rubik's Cube blindfolded. On the other hand, you might think that air could reduce heat transfer by blocking light, leading to lower temperatures. It could increase heat transfer due to its insulating properties, which aren't as effective as a vacuum. This has nothing to do with the light energy transfer, but instead revolves around energy transfer through convection. Now, imagine a thick atmosphere sprawling throughout the entire solar system. It's like a cosmic security blanket, insulating the outward heat energy transfer from the sun and potentially lowering temperatures on Earth. Here's another nugget of cosmic trivia. Stars boast a convective zone on the outside and a radiative zone on the inside. It means that conduction, or rather advection, is just as important as radiation. So, introducing an extra layer of air might improve this conduction game. Yet, the workings of extending the atmosphere and introducing gas into the solar system remain a cosmic enigma. Some stars out there rock an extended atmosphere. This atmosphere tends to be chilly due to dust gobbling up stars' radiation. It's like a condensation party zone where molecules can hang out and have a blast. But these stars also have some size to them, reaching as far as Earth's orbit. And at Earth's orbit, things would get steamy. Next up on this wild cosmic roller coaster, the Moon decides to take a leisure break and comes to a complete stop. Oh boy, that's when things really go off the rails. Earth's gravity pulls the Moon closer and closer, leading to an epic collision of cosmic proportions. Buckle up, my friend, because surviving scorching heat would only be the beginning of the end for our poor planet. It would be ripped apart, and the rest of the solar system would also go through some tough times, especially with all that air in the mix. In fact, brace yourself for a mind-blowing twist. Our once harmonious solar system could morph into a cosmic black hole. Why, you ask? Well, it's all because of the massive amount of air we'd have floating around. This air has weight, my friend, and with the heliosphere stretching a whopping 90 astronomical units, we're talking about a whole lot of mass, roughly 5 billion times more than the mighty Sun itself. Now, if the Sun's gravitational pull decided to gather all that mass and compress it, the solar system would become denser than a crowded interstellar party. Imagine squeezing all that air into a space about 80% of Earth's diameter. Dude, you'd witness the birth of a black hole right in front of your eyes. But let's be real here. Surviving that mind-boggling scenario is about as likely as finding a unicorn riding a flying saucer. So, fasten your seatbelt and enjoy the cosmic spectacle from the comfort of your imagination. For this journey through the bizarre reaches of the universe is nothing short of an electrifying adventure. In the end, we're left with more questions than answers. The intricate dance between air, heat, and the vastness of space remains an elusive puzzle. It's a game where the rules are yet to be discovered. So, let your imagination run wild and keep on pondering the wonders of the cosmos. If I were an astronaut and discovered that we could breathe in space, I would work with my crewmates and mission control to establish protocols and safety measures for operating in this newfound environment. Although breathable air would eliminate the need for spacesuits, other potential hazards might still exist, such as temperature extremes or radiation, which would require appropriate precautions. Then I would examine if the air was abundant and sustainable. Plus, I would explore ways to utilize it for various purposes, such as oxygen generation, atmosphere regulation in spacecraft, or even potential fuel production for long-duration missions. And what would you do in such a situation?
You know, oceans cover around 70% of Earth's surface, and we have only explored 5 to 20% of them. And now, astronomers have found more water, a huge stash floating out there in space by a quasar that's more than 12 billion light-years away. And we aren't talking about just a little puddle. It's a mind-blowing amount of water, about 140 trillion times more than all the water in Earth's oceans combined. It's hanging around a supermassive black hole that's a staggering 20 billion times bigger than our Sun. This black hole is surrounded by a super bright quasar, It gives off as much energy as you get if you gathered 1,000 trillion suns. I can't count that high. Oh, by the way, since light takes time to reach us, we're seeing this quasar as it was when the universe was still very young. Astronomers are sure that the newly discovered water reservoir is the farthest and biggest we have ever found in space. Mark Bradford from NASA's Jet Propulsion Laboratory explains that the environment of this quasar is so unique that it's capable of creating an incredible amount of water. Bradford's team, along with another group of astronomers, has been studying the quasar and the supermassive black hole at its center for quite some time. They've noticed that as the black hole pulls in surrounding matter, it heats up the nearby gas and dust. This process has created a region packed with molecules that have never been observed at such a great distance before. Now, quasars were first spotted around 50 years ago, when telescopes picked up super bright objects way out in space. They're not regular stars. They shine from the centers of distant galaxies and are so powerful they outshine all the stars in their galaxy combined. At the heart of every quasar is a gigantic black hole, which is millions or even billions of times heavier than the Sun. When gas and dust swirl toward the black hole, they heat up and release an insane amount of energy. It makes quasars some of the brightest and most powerful things we've ever seen in space. Looking at quasars is like looking back in time. The light we see from them today has been traveling for billions of years. It gives scientists a peek at what the universe looked like way back in the past. Quasars can help us understand how galaxies formed, how matter spread out, and how the first cosmic structures came together. Some quasars shoot out massive jets of superfast particles. Stretching across space, they can sometimes change entire regions of the universe. But let's get back to that space water, or rather water vapor. When astronomers discovered it, it was floating around the quasar, spread across a huge area hundreds of light-years wide. For comparison, just 1 light-year is about 6 trillion miles. Even though the gas there is incredibly thin, unlike what we're used to on Earth, it's much warmer and denser than the gas found in most other galaxies, including our own Milky Way. The temperature of this gas is around -63 degrees Fahrenheit, and it's about 300 trillion times less dense than Earth's atmosphere. It does sound extreme, even in space terms, it's unusual. Now, water vapor isn't just another molecule. The very fact that it exists near the quasar hints that the area is regularly blasted with radiation. That's what keeps the gas warmer than usual. To add to the mystery, astronomers also found carbon monoxide and other molecules. In other words, there's plenty of raw material floating around. In the future, this gas could help the supermassive black hole grow even bigger, up to 6 times its current size. But that's just one of many potential scenarios. Some of the gas might get pulled into the black hole, some could form new stars, and some might even get flung out into space. Now, finding water vapor in such a distant quasar means that the basic building blocks of the universe have been around for billions of years. Water is crucial for life as we know it, so its presence so long ago hints that the ingredients for life existed much earlier than we might have thought. But water isn't just important for life. It also plays a key role in how stars and galaxies form. When giant clouds of gas cool down, water helps them collapse, making it easier for new stars to be born. But how did researchers even spot this massive cloud of water? In 2008, Bradford's team started looking for water in space with the help of a special instrument called Z-Spec. It was attached to a 33-foot telescope in Hawaii. To double-check their findings, they used another powerful tool, CARMA. That's a group of radio dishes in the mountains of Southern California. At the same time, a different team was searching for water using a telescope in the French Alps. In 2010, the second team found a small hint of water in the distant quasar. It was just one teeny-tiny signal. After that, Bradford's group detected more signals. It was all the proof we needed to conclude that an enormous amount of water was actually out there. Now, our floating cloud of water vapor isn't the only place where we've found water beyond Earth. Scientists have recently made a huge discovery. It turns out there are massive reserves of liquid water hidden deep underground on Mars. So, in theory, future astronauts could use this water to support missions or even make Mars a long-term home. But of course, there's a catch. This water isn't sitting in nice, accessible lakes or oceans. It's buried so deep inside Mars that we have no way of reaching it with current technology. Scientists have figured this out by analyzing seismic data from the Mars InSight lander. It picked up some strange seismic activity, and the best way to explain it is by these hidden water reservoirs. Mars still does have some water today, mostly as ice on or just beneath the surface. But that's nothing compared to the massive amounts of water the planet had billions of years ago. The big mystery is, where did all that water go? Scientists think it could have either escaped into space or moved into the planet's interior, where it might now be trapped as liquid reservoirs or ice deposits. The problem? We have no way of measuring how much water Mars lost. So for now, that question remains unanswered. Earth's moon has water too, but not in the way you might think. Instead of lakes or rivers, the moon's water is mostly frozen ice, spread out unevenly across the surface. The cold, shadowed poles are especially full of it, since they never get sunlight. A lot of this ice is also mixed in with lunar soil and buried deep underground, making it super tricky to get to. Then there's Enceladus, one of Saturn's moons. It's tiny, just 314 miles across. It's small enough to fit inside Arizona. I think we should try that. Anyway, when NASA's Cassini space probe arrived at Saturn, scientists expected Enceladus to be a barren, frozen world. But instead, they saw huge plumes of icy particles and water vapor erupting from geysers near the South Pole. That meant there had to be a massive ocean hiding beneath its icy shell, sandwiched between the moon's rocky core and the frozen surface. The fact that this ocean is active and constantly sending material into space makes Enceladus a top candidate for future exploration. We also have Europa, one of Jupiter's moons, and one of the most promising places to search for alien life. Europa has a gigantic saltwater ocean that could be 40 to 100 miles deep. This means it might hold more water than all of Earth's oceans combined. But there's a big obstacle. This ocean is hidden under a thick ice shell, which scientists think is 10 to 20 miles deep. Europa's ocean stays liquid because of tidal forces from Jupiter's gravity. The planet's massive pull stretches and squeezes the moon, creating friction, which heats up the interior, stopping the ocean from freezing solid. And the most exciting part is that scientists think water plumes might be erupting from cracks in Europa's ice, shooting ocean water into space. Now, if that's true, we could potentially sample the ocean without having to drill through miles of ice. But there are still a lot of unknowns. How big are Europa's water reservoirs? How quickly do they refreeze? And how does the intense temperature and pressure affect the ice? Scientists are eager to figure this out because Europa's ocean is one of the best bets we have for finding extraterrestrial microbes somewhere in our solar system.
It's September 1977. You're playing one of the first video game consoles released in North America. You step outside and see the whole neighborhood waiting for Voyager 1 to launch. It's a super sunny day, so you squint a little, trying to see what's happening. You live in the neighborhood right outside the launching station. You get yourself some food and watch the Voyager take off into space. You're so impressed, you decide to dedicate your career to working with NASA. 35 years later, you're now a senior official in NASA, specializing in Voyager 1. It's 2012, and you're sitting in the control room with your colleagues. Everyone is staring at their computer screens as they work on the Voyager. You're sitting on the top, overlooking everything and making sure all systems are in check. This day is special, as Voyager 1 is about to exit the heliosphere, which is a science word for the outer shell of our solar system. It's a bubble of space affected by the solar wind, which comes from the sun. By 2021, it got 14 billion miles away from Earth, which is equivalent to 153 astronomical units from the sun. One astronomical unit is the distance between the Sun and the Earth. The craft was originally meant to fly by Uranus, Saturn, and Jupiter, and toss itself from one planet to another with the use of their gravitational pull. Everyone is impatiently waiting for it to exit the heliosphere. 3, 2, 1, and it's officially out. All systems are normal and functioning. You praise your team for doing an excellent job. With Voyager 1 reaching this far, there's still tons to explore in outer space. You were once a young adult watching the craft launch outside your neighborhood, and now you're the main person in charge of the operation. 9 years later. Since Voyager 1 left the heliosphere, you've been checking up on it every now and then, making sure all systems and functions are in order. It's been sending back measurements of the interstellar medium. It's the area between the stars of our galaxy, consisting of ionized materials. Ionized is basically a simple version of a molecule or substance. The interstellar medium is an electrically charged state of plasma, or ionized plasma, and is very unstable. It's like going from lightning in a thunderstorm back to calm rain in a matter of seconds. The plasma up there is different than the plasma on Earth, in that it's difficult to filter out. There are around 0.06 atoms for every cubic inch in the interstellar medium. The air we breathe on Earth has billions of atoms. By measuring the plasma in the interstellar medium, we can further understand the behavior and structure of chemicals and gases. It's possible that the oxygen we know and love on Earth is different than the ones out there. One of your main tasks is to learn more about how the solar wind from the Sun and interstellar medium interact with each other to create the heliosphere. So, after doing some routine checkups and other maintenance work on Voyager 1 from the control room, you notice something strange coming from the screen. You sit in front of the computer, crunching the numbers of the plasma vibrations and convert them into an audio file of about 3 kilohertz. You click on it and listen to an eerie, subtle hum. You and your team are surprised that these vibrations occurred in such a small frequency. Given that space is massive, something like this might mean life on other planets. Everyone else at the station rushes to the control room to listen to that sound from outer space. It's monotonous and faint, but it's definitely coming from outside the heliosphere. You run the numbers over and over to make sure it's not a fluke, but it's on point. You make sure your team doesn't spill the beans to anyone outside until everything is known and clear. You get into beast mode with work and try to catch the sound again, and it remains. You can't sleep trying to think of something that could be producing this hum. A few days pass by, and the sound is pretty consistent. If there was some life out there trying to communicate with you, then surely it would have said something that can be deciphered. You analyze the audio files once again, trying to see if it's some phonetic language you don't know. You call in a linguist to see if she can make something out of it. You and the squad gather around, waiting impatiently for some answers. After a while, she believes that it might be someone out there communicating with us, but the only way to find out is by sending something back to them. You arrange a meeting with your team and try to figure out what message you can send. After much thinking and lots of coffee, you decide to send them one phrase in English. Who are you? You send out the signal through Voyager 1 and wait for any changes in the hum, but you don't get anything straight away. It may take some time for a response. You wait all night, and still, there's nothing. It's starting to look like there isn't anything out there. For the next couple of days, you keep sending out phrases for anything to pick up. Since space is a vacuum, sound waves can't travel, so sending out voice messages on a large speaker won't work. You locate the source of the humming and aim for it when sending the audio file. Every day, you send something different, but still, you don't hear anything from them for a week. It seems that intelligent life in the distant world isn't real. The areas between the star systems in a galaxy aren't necessarily a complete vacuum. That's where the interstellar medium is. It contains gases, dust, and cosmic rays, which are energy particles. After many months of this constant humming being produced, you still try to figure out what's going on. You sit there, remembering the time when the Voyager was first launched. You remember running outside after playing some video games. You couldn't see properly because of the sun, and you freeze in your spot and have a eureka moment. You go through some notes taken in the past. The answer was in front of you all this time. Every now and then, the sun sends a burst of energy that causes the plasma of interstellar space to vibrate. Scientists can measure the frequency of waves when the plasma vibrates to show how close they are to each other. And on the day when the hum was delivered, there were some irregular frequencies coming from the sun. So that hum might have been the plasma vibrating in a weird way because of the sun flares. But these low-level vibrations last longer than quick jumps and spikes. They're fainter. You run the tests again and find out that it's not some intelligent life forms out there trying to talk to you. It's the little vibrations caused by sun flares. You notify your team about this breakthrough, and everyone's celebrating. But after all these tests and research, you still don't know why plasma in the interstellar medium vibrates in such a way. Those answers will have to wait. 2027. It's been 50 years since the launch of Voyager 1. You're way into your senior years and just retired from NASA. You have many scholarships in your name and programs for young people who want to learn about space and science. You go back to the control room once more, where you thought you had discovered intelligent life on a distant world. Then you remember all the good times you had. You say goodbye to everything, knowing that this is Voyager's final moments. It was built to last up to 50 years. After that, it'll just be a floating object in the vastness of space. It's already surprising to know that this is Earth's most distant object from us, but it's time to let others take your place. You shut off the lights and close the door. The Voyager makes one last beep before eternal silence.
Humans could live in a vacuum, with the only difference being, well, our entire selves. We're always talking about living on other planets and how we can adapt to them, but theoretically, we could live on a space station. However, in that case, life would evolve completely differently, all because we'd have to live without an atmosphere. What do we humans need to adapt to living in a vacuum? Dougal Dixon created this cool concept in his book, creatures known as vacuumorphs, designed to survive in space. They're kinda like humans, but not really. First, in space with no air at all, it's all about pressure. There's a thing called atmospheric pressure. In simple words, how much does the atmosphere press on our shoulders? How heavy it weighs. Humans are used to living at sea level where there's a lot of pressure from the air around us. But in space, there's none. This would be tough for our bodies. Astronauts have their suits to handle such dramatic change. Which means, most likely we'd have to get a hard shell guarding our insides, like robots, beetles, or certain marine animals that can handle different levels of depth. Having a shell of some kind also helps to control the movement of atoms both coming in and leaving the body. These unique beings from Dixon's book, Homo caelestes, have crustacean-like features. You can see that they have this shield we discussed. They're built to withstand the challenges of orbit and the vacuum. They breathe with 3 lungs, have stubby limbs for grabbing onto spaceships, and sealed eyes to shield them from harsh conditions. These little guys also need unique organs to handle oxygen and waste. Unfortunately, they can't reproduce. Despite their incredible adaptability, vacuumorphs are sterile and have a limited lifespan. We know from movies that outer space is extremely scary. It's freezing cold, dangerous radiation, and no air at all. If you're out there, your blood boils or you simply freeze instantly. But despite all that, humans could survive in outer space for a while. Imagine you're suddenly thrown out of your spaceship. In movies, that would mean instant departure from the life station. But in real life, it's not as instant as Hollywood makes it seem. Scientists have done questionable experiments and had accidents with humans. There was an astronaut who had his spacesuit accidentally depressurized. He blacked out, but was luckily okay after repressurization. although he did lose his sense of taste for a while. In any case, it turns out you could actually survive for a couple of minutes in the vacuum of space, but it's not a pleasant experience. When you're in space without a suit, the lack of pressure makes air in your lungs expand, which is really bad if you're holding your breath. Within a minute, you'll pass out from lack of oxygen. It takes just a few seconds for everything to go dark. However, there is a form of life that can hang out in outer space just fine. Scientists found some tiny creatures called Extremophiles that can handle all of that. They're nature's most brave survivors. These microbes can handle crazy conditions like freezing cold, no air, and lots of radiation. Recently, we decided to find out how this special bacterium copes in space. Scientists sent it up to the International Space Station and left it outside for a whole year. When they checked on it later, they found something amazing. The bacterium hadn't changed much in appearance, and it even had produced tiny structures called outer membrane vesicles to protect itself. It turns out that this bacterium has a superpower. It can repair its DNA and fight off harmful molecules that could damage it. It also changes the way it uses energy to adapt to space life. This could help us learn more about how life can exist beyond our planet. It was called the Transpopo mission. Bacteria are incredibly adaptive. For example, we discovered that bacteria can float around in space for years. These tiny organisms can stick together in clumps, like little protective communities. They can survive the harsh conditions of outer space by doing so. In a cool experiment, scientists put some really tough bacteria on the outside of the International Space Station. These bacteria were in little balls, each 5 sheets of paper thick. As a result, they stayed out there, unharmed, for 3 whole years. Their outer layers acted like shields, protecting the ones inside from all the space nasties. This discovery suggests that groups of bacteria could travel through space between planets. They call this idea Panspermia, which basically means spreading life through the universe. In other words, space travel might accidentally bring life to other planets. So if we found microbial life on Mars, for example, that could even signify that it had arrived there from somewhere. All this means that some microbes could survive in outer space. With more complex creatures like animals, however, things get harder. The most important thing for sustaining life is energy. Everything else is a nice addition, but without energy, we wouldn't get anywhere. Life also needs a lot of chemicals mixed in a liquid for a long time and in a big space station to function. If there's not enough pressure, the liquid evaporates. Vacuum means there's hardly any pressure at all. Life evolving inside an asteroid or moon that lacks atmosphere might be possible. Life adapting to space is possible. Hypothetically, these space-living beings could be made of gas, sentient clouds floating around. They could also be made of pure energy, invisible but able to communicate through their energy levels. Or some giants with their own atmosphere, like Earth, with smaller creatures living on them. But all this is extremely unlikely, so the chances that life will evolve in outer space by itself are super low. Now, imagine if, instead of space, we were talking about a planet covered in a tough, non-breathable layer around it. Surprisingly, even if there's no air on the planet, there are still some chances that life could evolve. At least if there are some signs of water. Deep below the surface, there could be rivers warmed by special vents spewing out minerals. Life could start there, away from the surface where it's safe from drying up. Breathing is just one way we get energy, but there are other options. For example, sunlight. Think about the moon's surface. There's no air there, but we could still use solar power to survive. However, we're deep underground. With limited access to sunlight, these creatures would have to evolve ingenious ways to harness alternative energy sources. Some of them could possess photosynthetic capabilities, using specialized pigments to harness even the faintest traces of light filtering through the planet's crust. Others could form symbiotic relationships with certain bacteria that could help them receive energy from minerals and organic compounds in the rivers. Deep below the planet's surface, the rivers aren't just sources of water. They're rich in nutrients vital for a sustaining life. These rivers flow through vast underground networks, creating pockets of habitable environments where life thrives. These creatures could eat solid minerals and develop shells to keep their insides moist. They'd have to evolve unique biological features to survive in their harsh surroundings. For example, some species might develop bioluminescence to navigate the dark underground tunnels. Others could adapt sensory organs capable of detecting subtle changes in the environment, helping them locate sources of nutrients and avoid danger, kind of like moles. These ecosystems would operate on a delicate balance of nutrient cycling. Microorganisms would break down organic matter and release essential nutrients into the rivers. This, in turn, could help plants evolve, and plants could become food for larger creatures, and so on. And then, who knows what could happen over millennia? As the planet's crust shifts and cracks over time, exposing these underground realms to new challenges, the creatures adapt and evolve in response. In any case, what we learned is that life is much more adapting than we previously thought. It could survive even in extremely harsh conditions. We might not know what types of life we'll discover on other planets, but we shouldn't be surprised if we find it in weird, unexpected places.
No one will hear your cry in space, or something like that. We've all heard this famous, chilling phrase, and it's actually true. Space, for the most part, consists of a giant nothingness. There's a lot of, space in space. But this doesn't mean there are no sounds in space. In fact, there are plenty of them, and some of them can even make you shiver. Let's take a look at the scariest space sounds. First of all, how are cosmic sounds even recorded? Sound is just the vibration of molecules. When you scream, you make the molecules push each other furiously until they reach the ear of the person you're yelling at. Then these vibrations get transmitted to the brain, and we recognize them as something that you might need to apologize for. In other words, to hear something, we need molecules. And that's where things get complicated. There aren't any of them in space. The entire universe almost completely consists of a vacuum. No, not a Hoover. Absolute nothingness. However, the wizards from NASA still record space sound somehow. So how do they do it? The thing is, there are some types of waves that don't care about molecules. We regular folk can't perceive them without some special devices. These waves include, for example, radio waves. We'll need a radio or something like that to recognize them. And that's exactly what NASA's satellites do. They catch random radio waves. Thanks to their heroism, we can find out how different cosmic bodies sound. These satellites record a variety of waves, fluctuations of plasmas, magnetic fields, and other, stuff. And then scientists from NASA transform all this into normal soundtracks. And some of them sound quite frightening, to put it mildly. Let's take our magnetic field, for example. It surrounds our planet like an invisible shield, protecting us from all sorts of nasties, like radiation and solar winds. At the same time, we can neither see it, feel it, nor hear. Oops. Well, the last one is outdated. Scientists from the Technical University of Denmark took magnetic waves recorded by the ESA swarm satellite. They converted them into an audio track and got a pretty creepy result. Now, to be honest, it sounds more like an eerie entity stalking you in the middle of the night. And if you remember the maps of Earth's magnetic field, it starts to feel like a spider crawling nearby. Ew. And this isn't the first strange sound that we caught on Earth. Recently, we caught another weird radio emission from space. Scientists found out that the repeating signal came from somewhere very far away, like billions of light years away from us. Such fast radio bursts usually lasted no longer than a few milliseconds, but this one was unique. It lasted about 3 seconds, basically thousands of times longer than usual. And at the same time, the signal was very precise, so much so that scientists even compared it to a heartbeat. Scientists believe that this signal is caused by pulsars, or neutron stars. One time, Nikola Tesla caught something similar. But unfortunately, at that time, we didn't know about such things as pulsars, so Tesla was sure that he had caught a message from some extraterrestrial life. It's a pity that the truth turned out to be much more boring. But let's move on from the Earth to the Moon. In 1969, the astronauts of the Apollo 10 mission, the spacecraft that made the final test flight to the Moon, flew past its surface. And then they caught some strange signals coming from the dark side of the Moon, the side that we never see because the Moon is tidally locked to us. The sound was so weird that the astronauts weren't even sure whether to report it to NASA. They were afraid they wouldn't be taken seriously, and maybe even not allowed to participate in the next space missions. Here's what it sounded like. But according to NASA, it's not some creepy extraterrestrial music at all. These may just be some radio waves that affected each other because of their proximity, although the astronauts who heard it for the first time probably felt a little creeped out. Let's move to the other planets. Now, 40 years ago, scientists actively explored the surface of Venus. They sent as many as 10 probes there, which were supposed to capture audio and video shooting from the surface. Now we know what Venus, which could easily destroy us at any attempt to even get close to it, sounds like. Horrifying. And you wouldn't expect anything else from the most dangerous planet in the solar system. Unfortunately, Venus is even more toxic than the average Twitter user. So these probes didn't last too long. They heroically arrived on a planet and soon broke down. Next one is Jupiter. This space giant, which is 11 times larger than the Earth, never fails to scare us. One of NASA's probes, Juno, flies around Jupiter every few weeks. The probe is moving at a tremendous speed, 130,000 miles per hour. One day, Juno caught one of the strongest invisible signals it had ever encountered. This was the point at which the mad solar wind came into conflict with the magnetic field of Jupiter. It kind of sounded like a cosmic boom. The original sound lasted 2 hours, but it was compressed to a few seconds. It actually sounds more like a collision of a sea wave and a rock. But here, in terms of horror, Jupiter surprisingly loses to one of its small moons, Ganymede. In 2021, the Galileo space probe flew past Ganymede, and during its flight, it received a rather strange recording. These sounds are satellite radiation, and it's unclear whether it sounds like a cozy sunny day in the jungle or like thousands of bats waiting for you in the night. Next one is Saturn. This signal was caught by the Cassini-Huygens Automatic Interplanetary Station, which was launched into space in 1997. When flying past Saturn, Cassini recorded a pretty scary sound. This terrifying cry of thousands of souls is actually just some radio waves. They aren't too different from what the auroras emit on Earth. A little later, Cassini received another recording, the sounds made by lightning and thunderstorms on Saturn. They sound pretty interesting, too. More like popping corn or a Geiger counter, right? But that's just because these lightning strikes have a crazy frequency. Moving on from the solar system to outer space. The famous Voyager 1 was launched back in 1977 and continues to send us data even 40 years after its launch. In 2012, it left the solar system and entered interstellar space. And then, while abandoning its home, Voyager 1 detected the sound of plasma waves. The original recording lasted 7 months, but fortunately, scientists felt sorry for us and reduced it to 12 seconds. It isn't really eerie, but is still kind of unsettling. And although it feels like nothing can beat Saturn's horrors, let's end this tournament with one of the scariest objects in the universe, a black hole. This sound was recorded by the Chandra Space Telescope. While studying a cluster of galaxies in the constellation Perseus, they discovered something strange. Some undulating movements appear from the center of the cluster. They spread out in all directions, like circles on the water. Scientists have suggested that this was caused by a supermassive black hole. The thing is, black holes don't always devour space objects entirely. Sometimes they kind of spit them out. This causes vibrations of gases, which we can convert into soundtracks. What's interesting is that the oscillation of each such wave actually lasts about 10 million years. You're just listening to a very accelerated recording. Scientists have reduced the delay between oscillations by about 144 quadrillion times. So let's check it out. This is probably the eeriest sound from the whole list. Nothing too loud or wild, but there's something dark and disturbing about it. Now, those were the scariest space sounds captured by NASA. To be fair, most of them sounded creepy simply because they're radio waves, but it's still fun to get spooked sometimes.
Oxygen, as well as the process of breathing, is crucial for our survival. You breathe every minute and every second of your life without even thinking of it. But there's next to no molecular oxygen, which we also know as O2 in space. Interestingly, in 1998, NASA sent to space a satellite whose main goal was to find loads of molecular oxygen. But it never did. Then scientists, worried that something could be wrong with the spacecraft's equipment, aimed it at Earth. And guess what? Right, the instrument showed there was plenty of oxygen there. Now, we know why these life-giving molecules are so rare in space. All because oxygen clings to stardust so tightly that it prevents its atoms from joining together and forming oxygen molecules. That's actually the answer to the intriguing question of why we can't breathe in space. There's simply not enough oxygen there for this process to happen. And even if you went out into open space with your own oxygen inside your lungs, it wouldn't help you. In the low-pressure environment of the cosmos, this air in your lungs would expand incredibly fast, making the lungs burst. So that's what would happen if you went to space and decided to walk around without a spacesuit. But that wouldn't be the only tragic consequence. The oxygen in the rest of your body, for example, in your blood, would also expand, making you balloon up to 2 times your normal size. Luckily, your skin is elastic enough, and it would hold your body together. Then, all the exposed liquid on your body would start to vaporize, making it very uncomfortable for, let's say, your tongue and eyes. Since there would be no air in your lungs, your blood would stop sending oxygen to your brain. That's why you'd pass out in around 15 seconds. A few more dozens of seconds, and the lack of oxygen would lead to tragic consequences. Interestingly, we often imagine outer space as a freezing cold and inhospitable place. We believe that if someone ended up there without a spacesuit, they would immediately freeze into a human popsicle. It's a good thing we're on Earth. You can take a deep breath and subscribe to our channel. In reality, though, the cosmos itself doesn't have temperature. You see, scientifically speaking, temperature is a function of heat energy in a given amount of matter. But here's the catch. Space doesn't have any mass. Plus, heat transfers can't happen in space in the same way as they do on Earth, conduction and convection, because they simply can't occur without matter. Let's get practical. What does the fact that space basically doesn't have temperature mean for a person without a spacesuit floating in the darkness of the cosmos? Let's imagine there is enough oxygen in space, and this person can breathe. Will it help? In space, thermal radiation, which is the heat from the sun's rays, is the main means of heat transfer. So, if this astronaut without a spacesuit was directly exposed to the sun's radiation, they would feel slightly warm or slightly cold if shaded from sunlight. In the latter case, the person's own body would be radiating away heat. But what if they ended up in deep space, where temperatures drop down to minus 455 degrees Fahrenheit? That's the temperature of the cosmic microwave background, the leftover from the Big Bang, permeating the universe. Our astronaut would still not freeze instantly since heat transfers don't occur very rapidly by radiation alone. But the absence of normal atmospheric pressure, which is the one at Earth's surface, would be a much greater concern. The main problem would be the risk of lung rupture due to air expansion. And there's also something called ebulism. That's when reduced pressure of the environment lowers the boiling temperatures of body fluids. As a result, liquid water in the bloodstream and soft tissues turns into water vapor. So even if humans could breathe in space, it wouldn't change anything in the grand scheme of things.
In the icy wilderness of Antarctica, there was a peculiar rock. Amidst the vast, smooth, and snowy landscape, it stood alone like a dark smudge. This rock had been there for ages, untouched except for occasional snowfall. Roberta Score, a lab manager at NASA's Johnson Space Center, had spent countless hours in Antarctica searching for rocks just like this one. Antarctica was an unexpected treasure trove for these discoveries. These rocks were easy to spot against the blindingly white ice. Why was it so important? Because it wasn't just any rock. It was a meteorite that had fallen from space thousands of years ago. Roberta's rock, known as ALH841, was initially unimpressive. However, it turned out to be extraordinary. It was a piece of Mars. The rock's chemical composition perfectly matched the surface of the red planet. Turns out, it had been blasted off Mars during a colossal collision millions of years ago. It was wandering through space before landing on Earth. There, it had remained undisturbed for a very long time. Scientists at Johnson Space Center carefully examined this Martian visitor. Years later, physicists made a remarkable announcement. This meteorite contained tiny structures that looked just like living organisms found on Earth. NASA immediately shared this discovery with the world. We found fossilized evidence of life on Mars. However, as other scientists got their hands on the rock and conducted further studies, they began to doubt it. Yes, it was a fascinating piece of rock, but Martian chemistry might create similar structures without life being involved. So, unfortunately, it wasn't conclusive evidence. But all this debate raised a very important question. Would we recognize extraterrestrial life if we saw it? There are more than 200 different definitions of life in scientific literature. So, what should we be looking for? To figure out what makes something alive, scientists have come up with 3 important things that living things must have. First, living things need to store information about themselves. This information tells them how to work and what they're like. It's a bit like having a set of instructions for how they function. Second, they need to be able to interact with their environment and create reactions. These reactions help them get energy, move around, and respond to changes or dangers. Lastly, they must be able to make copies of themselves, reproducing, and making other things that are just like them. This ability is a big part of what makes something alive. The famous physicist Erwin Schrödinger was one of the first people to figure this out. He said that storing, using, and passing on information is super important for life. It's like a cycle. Information helps create reactions, and some of those reactions let living things make copies of themselves. On Earth, we see this in action. We humans, for example, have DNA to store our information. It helps us with our evolution. Thanks to all this, we can adapt to our surroundings over time. Nature sees that some traits are helpful for survival, so they stick around, while others get left behind. In other words, a way to define life is by saying that it's subject to this process called Darwinian evolution. But how did it happen that things capable of evolution appeared? And when did the very first life emerge in our universe? To find out the answer, let's go to the very beginning of everything. The beginning was the Big Bang. Right after it, there were no stars or galaxies. The universe started as a mostly even and empty place, with just a tiny bit denser than the rest. After the first second or so, first protons, neutrons, and electrons, among other particles, appeared. And just about a couple of minutes later, these protons and neutrons came together to make stable atomic cores. Then, everything was a superhot soup of particles for about 380,000 years. It was way too hot to form anything dense. The universe needed some time to chill. After it calmed down a bit, it let electrons join these cores, forming neutral atoms for the first time. Finally, some comfy temperatures. If we were there, we wouldn't have needed the sun to keep us warm. That cosmic background radiation would have been enough. Could life appear at this point? Probably not. In those early moments after the Big Bang, The universe had only hydrogen, helium, a tiny bit of lithium, and almost none of the other elements life needs. Life, as we know, requires things like water and organic compounds, so it wasn't about the temperatures, it was about the ingredients. Now, everything had to form over time from these atoms. To create something like a planet, which is much denser than the universe on average, it needed a lot of time and gravitational squeezing. Gravity is the real hero of this story. It changed the universe completely. Even though it started slow, it kept going and got stronger. Regions that were a bit denser could pull in more matter, and the denser they got, the more they attracted. The very first star should have formed around 50 to 100 million years after the Big Bang. These stars could become incredibly massive, hundreds or even 1,000 times bigger than our Sun. And when these stars formed, it didn't take long, maybe 1 or 2 million years, before they disappeared. Just for comparison, our own Sun is 4.6 billion years old and still going strong. When huge stars reach the end of their lives, something incredible happens. They transform helium into carbon, then carbon into oxygen, and oxygen into a bunch of other stuff all the way up the periodic table. Then the star's core collapses, causing a massive supernova. This huge BAM releases all these heavy elements into the universe. Hooray! Now the space is filled with something new. The universe acquires many cool things, including the ingredients needed for rocky planets and organic molecules. Each generation of stars gets even richer than the previous one. Yes to more elements. It means more rocky planets, more essential ingredients for life, and more chances for complex organic molecules to form. And now, when the universe was around 300 to 500 million years old, rocky planets were already popping up everywhere. Great. Can we have some life now? That depends on what we see as life. The recipe for life, as we know it, needs a special ingredient, carbon. Carbon is special because it can bond with other atoms in so many ways. It can connect with different shapes to build all sorts of amazing complex structures. It's carbon that helps us form things like DNA and proteins, which are the building blocks of living things. Now, while the universe made rocky planets relatively quickly, it took a bit longer to get enough carbon floating around. It appeared about 1 to 1.5 billion years after the Big Bang. As soon as it appeared, the universe finally had enough conditions to create life as we know it, which is why scientists are searching for planets around these oldest stars in the universe. These guys definitely had enough time for evolution. But just because you and me are made of carbon and other elements from exploded stars, doesn't mean that all life should be. Scientists are open to the idea of alternative biochemistries. There might be non-carbon-based life that we don't know about yet. For example, blobby beings made of silicon compounds. It's carbon's neighbor in the periodic table. So, when and where did life truly begin? Unfortunately, we don't know for sure yet. Most likely, the universe started preparing for life shortly after the first stars formed. And if all life is carbon-based only, then it should have appeared 1 to 1.5 billion years after the Big Bang. The universe is 13.8 billion years old. Looks like it had plenty of time to evolve lots of microorganisms. So even if we made a mistake, and the mysterious meteorite was just a piece of rock, we shouldn't give up. The search for extraterrestrial life continues, and who knows? Maybe in the future, we'll finally know the answers to all these important questions. Until then, stay tuned.